In last video we have seen the introduction about breadth first search. In this video we will see about the algorithm, how the algorithm works in breadth first search. The BFS algorithm employs a queue data structures to manage the sequence of states to be explored. It starts by adding the initial state to the queue. The core loop continues as long as the queue is not empty. In each iteration, the state at the front of queue following FIFO is removed and checked if it is the goal state. If it is the search is successful. If not, the state is expanded to the generate its successor state, possible next state based on variable action. The successor are then evaluated if the successor had not been visited before it's added back to the queue, ensuring all the states at the current depth level are explored before moving to the next level. This systematic exploration guarantees finding the shortest solution to the goal if it exists within a finite branching factor. However, if the goal is located deep within the search space, BFS might explore many irrelevant branches before finding it, leading to potential inefficiency in such case. Advantages of BFS is it offers several advantages. It is complete algorithm, meaning it will find a solution if one exists in the problem space with finite branching factor, limited options per state. Additionally, if all the actions have the same cost, BFS will find the shortest path to goal because it explores all possibilities at the given deep before moving on. BFS is also relatively easy to understand and implement due to its clear level-by-level exploration strategies. Next, we will see about the disadvantages. While BFS offers advantages, it also has limitations. The advantage algorithm can be memory intensive because it stores all the explored state in the queue. This can be a challenge for problem with large branching factor, where each state has many successor states. Additionally, BFS might not be most efficient approach for problem where the goal is located deep within the search space. BFS systematically explores all level, potentially wasting effort on irrelevant branches before finding the goal. Next, we will see about the depth first search. It is also a type of uninformed search strategies. DFS is fundamentally uninformed search strategy that explores the search space by following a single path as deeply as possible before tracking and exploring alternate branches. This presentation we will see about the DFS in AI. What is depth first search? Depth first search is an essential uninformed search technique used extensively in AI. Unlike informed search that leverages domain knowledge or heuristics, DFS explores the problem space without prior knowledge about its goal's location. It follows a depth-first exploration strategies. In each iteration, DFS expands the successor state, possible next states based on available actions of the current state. It continues to explore this path deeply, adding these successor states to the stack. That is last in first out that we use in the data structure. If DFS reaches a dead node, no successor states are valid or lead to the goal state. It backtracks by removing the top element from the stack and exploring alternative branches from the previous state. This approach can be efficient for specific problem space where the goal is likely located along a depth path. However, DFS might not be optimal for finding the shortest solution in all scenarios. Next, we will see about the algorithm, how it works. The DFS algorithm employs a stack data structure to manage the sequence of states to be explored. It starts by adding the initial state to the stack. The core loop continues as long as the state is not empty. In each iteration, the state on top of stack follows LIFO, that is last in first out, is removed and check if the goal state is reached. If it is, the search is successful. If not, the